In this video, we will consider an application of the dot product from physics. Work is defined as the energy transfer that occurs when an external force moves an object through a displacement. So let's sketch a force vector and a displacement that will occur. And since we can define the dot product to be the work, then we're really interested in the angle between these vectors. As a result, I'm going to make the displacement vector horizontal. So here we have some force being applied to an object. Maybe the object is here at the source. And as a result of applying that force vector, there's a displacement in the object. Only part of the force vector contributes to the work done on the object in displacing it by magnitude d. In order to see how much of that force is responsible for creating the work, we can decompose or resolve the force vector into two perpendicular components. One component is a horizontal component of the force vector with a magnitude or an amount of f sub x. And if we were to think of that as a vector along the horizontal axis, it is in the direction of the I hat. We also have a vertical component with an amount of f sub y in the direction of the j hat vector. And therefore fx I hat plus fy j hat is equal to the force vector F. And so we can see it is only the Fx I hat component which contributes to the work done. So the work that we are finding, F dot d, is the same as the Fx I hat vector dotted with the displacement. But the point about the I hat and the d vector is that they are in the same direction. So we take the magnitude of the first times the magnitude of the second times the cosine of the angle between the two vectors. But fx I hat and d are in the same direction, so the angle between them is 0. And so we end up getting fx multiplied by d is the same as the work done by the actual force, because part of the work done by the vertical component is 0. But if we realize fx is the adjacent side of a triangle with an internal angle here of theta, and the magnitude or the hypotenuse of this triangle is f, then the fx magnitude is nothing more than f times the cosine of the theta. And if we rearrange that equation, we see that df cosine theta is the same as the dot product that we started with in the first place. So the point here is to notice that when we want to calculate work, we really need to find out the component of the force that is in the same direction as the displacement. Let's now apply this concept to an example. In exercise 8, a 10 kilogram block slides down a frictionless 3-meter long ramp that is inclined by 30 degrees. We want to calculate how much work is done by the force of gravity when the block accelerates down the ramp. So here we have a block, and this block has a center of mass here. We can assume that from there until the end, that is the displacement of 3 meters, and that's parallel to the slant side of the ramp. We also have a weight vector, which from the center of mass acts towards the center of the earth, and we have some angle between the two vectors. So we can put those two, well, we can put the force vector over here in the free body diagram. And we don't necessarily put the displacement vector here because free body diagrams are for forces. What we do need to do is to resolve that force vector that we've just drawn into its horizontal and vertical components. So I will copy that vector, place it over here in this rotated axis. What I'm essentially doing is saying that this is my surface of the ramp, which is the horizontal x-axis over here, which is my x-axis here after having rotated to make the plane in a standard position. And so I'm going to take my force vector and I'm going to rotate it so that it looks like it's in quadrant 3, angled the same amount that it was in the previous diagram. I'm trying to create the same angle between the vector and the nearest axis, which is the y-axis. So I think that looks okay. And from here I can see this force vector has a horizontal component and a vertical component that lie along the y-axis and the x-axis. So in order to resolve the force vector, we create a right triangle to each axis, and we can therefore see a vertical component of force F, we'll call that Fy, and we can see a horizontal component, which we will call Fx. Now it is Fx which contributes to the work done along with the displacement vector d. So just labeling all of our vectors, displacement and force, we can now come up with our work calculation as the dot product of force and displacement. And we will use the polar form, Fd times the cosine of the angle between the two vectors. The magnitude of force is given by Newton's second law, which is mass times acceleration, and so we have 100 kilogram meter per second squared, or 100 newtons, multiplied by the magnitude of the displacement, which is 3 meters, and multiplied by the cosine of the angle in between. Now, I've specifically not put theta in here as part of the formula, even though theta was given here, because the theta from the formula represents the angle between the displacement and the force vectors, and that angle is specifically up here. If we were to create a right triangle out of these two vectors, we would get two similar triangles, and therefore we would see that the theta is actually a measure of the angle of inclination at the bottom left-hand corner. The angle that we want is the complementary angle, and so it's going to be pi by 2 minus theta in this particular example. Theta is 30 degrees, and so 90 degrees minus 30 degrees is 60 degrees. And so we have 300 multiplied by the cosine of 60 degrees, which is 1/2, which gives us 150 joules, is the work done in this particular example.